Hey everyone, happy to have you all here again. Another exciting day full of hackathons. Full of workshops for the ongoing hackathon. For this one, we have a speaker that you've already met. We have Piotr, who spoke yesterday as well, and will continue on for today as well. Sending you an invite, Piotr. Thank you for using your surname this time, because once again, we have two Piotrs in the audience.
Can you hear me well?
Yes, I can.
Perfect.
How are you doing?
Thank you. Very good.
Ready for round two?
Sorry?
Ready for round two?
Let's see if you can see my screen. Can you?
Yes.
Perfect. Okay, so I think we're ready to set off. Okay, so just for people who were absent yesterday, my name is Piotr Mikołajczyk, and I am Peter, if you find it easier. And I am a blockchain developer at Aleph, as well as recently I was nominated to be a core contributor to the Ink language. And today I will have a pleasure to introduce you to a bit more advanced topic. It is interaction between a smart contract and its execution environment. Let's start with a simple question. So, firstly, let's consider this. What data the contract have access to? So, if we take a look at a hello world of the smart contracts, it is a flipper contract. We could have the feeling that the only information that the smart contract has access to are message arguments, so the input from the user who is calling the contract, and of course the internal storage data that contract maintains. However, if we were limited only this data, smart contracts wouldn't be so powerful as they actually are. So the thing that we are missing here is something called host functions. But as similarly to presentation, before we move on to the details of these host functions, I would have to take a brief recap of the architecture of the executing environment. So just to remember, yesterday we introduced this blockchain onion concept. So here is the diagram from yesterday. So just to recap the whole picture, when a blockchain node, for example, a validator, is trying to process a transaction, which can be a contract instantiation, well, this transaction will have to actually go through a whole technology stack, starting from this host binary, the outermost circle. So this is a binary that is run by a blockchain node. When any transaction has to be executed, processed, a runtime, meaning a state transition function, has to be spawned in a separate process. And if the transaction happens to be a smart contract interaction, another innermost execution environment has to be created. This is called a contract sandbox. And now, what we'll be talking about? Can you see my cursor?
Yes, we can.
Yes, perfect. So the thing that we'll be considering during this talk is the interaction between the innermost layer, this contract sandbox, and the circle, the layer that is the neighboring with it. It is the runtime. Okay. So runtime by default, by design, exposes to this contract sandbox a suite of a few, pretty like about 20, 30 basic functionalities, basic methods that contract can make a use of. And let's see for some examples. So this basic API that is exposed to a contract includes information like who is calling, who is performing the current call. The contract can also query what is its own account ID, how many native tokens it has, But also there are some actions that a contract may ask to be done. For example, a contract might want to emit an event to signal or to send some information about its work, about its progress, and for that we'll use this emit event message. Emit event function. Also, there are some other functionalities like some basic cryptography, so hashing bytes or checking some very simple signatures in a few standards. We can also push some messages to a debug buffer, and there are a lot of more. However, these that you can see in that slide are the most common, most useful, let's say. The other way you can view this concept is that this contract sandbox, which in Polkadot world for now at least executes smart contracts as a WASM, WebAssembly programs. This basic API is just adding some opcodes to a contract. So, for example, if you probably might have seen example similar to this one, our contract may have a message, a method called, for example, terminate, which will actually kill this storage, finish the contract lifetime, and send all the contracts balance to somebody, to some predefined account. And here we can see in both lines that we are using this self.env method. This actually will return an object which provides this basic API. So once we obtain this via self.env, we can call, for example, caller to retrieve the account ID of the contract or a person who is calling this message, and then we can terminate contract in a similar way via this env object, saying to terminate this contract and send all my balance or all my native tokens to this account. Okay. Now let's see. Okay. This gives us a lot of power. It makes our contracts more expressive. However, it still doesn't give us the whole power that we might want. Right? If we go back to this slide, we can see this method called transfer. This actually allows us to transfer some money from the contract to a target account ID. Right, but if we were about to study the whole basic API, we wouldn't find there anything related to, for example, staking. So if we were about to create a liquid staking contract, which performs some staking actions like bonding, unbonding, and similar stuff, we actually couldn't make it with just these opcodes. There are a lot of more usages. So, for example, considering transfer balance transfers, there is this only method transfer provided, but things like transfer keeping alive and more sophisticated, more complex API is basically hidden from a contract. So how can we give this power to a contract? Here we have to stop for a moment and redefine or see a runtime, a state transition function from a different angle. Previously, I've said that it is just a state transition function. It is, I mean, I'm not denying it, but we can take a look at it from the other perspective. And for the sake of this presentation, I'd like you to think about runtime as a collection of some methods, of some functionalities that the blockchain itself exposes to its users. And we can divide all these sub-functions of runtime into two families. The first family is what I would call a user API. So if you are a bit familiar with substrate architecture where we use palettes or modules of a runtime, then it would be just a union of all dispatchables, so public functions from every palette. So this includes, of course, token transferring, all the staking actions, vesting things, and anything related to governance, or of course, contract calling, contract instantiation, and all other stuff. So basically, these are all the methods that you as a human user, can call by sending a transaction to a blockchain. Okay, this is the first family, and well, you probably you probably have used it at least once, right? However, there is a second family, which we could call contract API, and this family of functions is dedicated to only contracts. So this might include, of course, it is runtime dependent. So for some runtimes, this contract API family will be just empty, but some runtimes might include here some advanced cryptography. So, for example, something from the ZK world, for example, snark verification or something like this. In more general, it would be outsourcing some computation, or we are not talking about outsourcing some actually arbitrary computation, which might be pretty heavy. But also, this contract API might wrap some things from user API, but for example, with bypassing standard restrictions or maybe enforcing even more limitations. Of course, it's pretty much runtime dependent. Okay. The very important difference is that the first family is for you. Usually, it is dedicated for human users. The second one is dedicated for contracts. From my experience, these concepts are pretty confusing. So let me recap it with some pictures. It might be a bit easier if somebody was confused for now. So we can we can ask which actor can call which functions, right? So if you are familiar with the first Shrek movie, you would probably be able to fill the table, or which character goes along with might get along with another. So the standard blockchain user, like a person, can only call the user API, this staking things, transfer token transfers, and so on. But a contract might call anything, both user API and contract API. And for this presentation, for this talk, we'll be considering on the second row. It is smart contract calling the first family or calling second family. And these two mechanisms have their own names. The first one is called runtime call. So we are calling the runtime as a standard user. And the second one is called chain extension, because the chain logic provides some extensions just for smart contracts. This is the naming. Let's start with the first one. So let's start talking about runtime calling. It's let's say a very, very easy example. So let's say that our contract wants to transfer native tokens using this API, this mechanism. Okay, so the first thing that we need to create or prepare is the call object. So this is very similar to a thing that you would do as a person, as a human user. To perform a token transfer on blockchain, you would have to build a transaction, sign it, and send it. And hopefully it will get to a block and it will be executed. And similarly, a contract will have to prepare a transaction. It is here just this call object. Here we create an object of this enum type runtime call, balances call transfer with appropriate values, and then we are using this self.env object, and then we are using a call runtime function from it with this particular call object. Now, Inc behind the scenes will encode this object properly, and then it will dispatch it just as it was a normal user who just posted this transaction to a chain. Okay. Well, you might, a good question would be, where can we have this, from where we can have this types, this runtime call or balances call? And well, this is very runtime dependent. In some situations, blockchain runtime developers, maintainers would expose these types to you. So you as a smart contract developer would just import these types, or if it's not accessible, you would have to actually define it, build very simple structures which are actually easy to find how to implement it, how to implement them. The crucial thing here is to take care of these indices of this of palette index and call index. I don't want to get into the details here. This is probably that you would want to ask runtime maintainers to just validate if these definitions are valid for a target chain. Okay. Now there is a very important notice here. I will give you 10 seconds to read this sentence. Now, what I wanted to underline here is that, well, you as a smart contract developer, you can use runtime calls, only those runtime calls that are allowed by the runtime. So in the runtime specification, runtime configuration, maintainers, blockchain developers usually set up some call filter. So they are explicitly saying which runtime calls can be made by contracts. This is for security reasons, right? Because it's not that every call is secure for contracts to be. It is not secure for the chain that any smart contract could call any arbitrary runtime dispatchable. So actually, if you are targeting, for example, a staking API, you'd have to ensure that the chain that you are targeting allows for this particular runtime APIs that you want to call. And if not, you have to you have to reach developers, the blockchain maintainers, and discuss how you can get along, how they can allow for whitelist these APIs that you really need here. Okay. Now let's see what are the advantages and disadvantages of this mechanism. So, well, I want to consider both pros and cons, not only from the smart contract developer perspective, but also from the blockchain maintainers, right? Because well, this is a two-side two-side contract here between the smart contract developers and blockchain maintainers. So we'll consider both perspectives, so you know what comes with this mechanics. So the biggest advantage of this mechanism of the runtime call is that for runtime maintainers, there's actually nothing to work on. The only action that they have to take is to allow for a particular runtime call to be made. So changing this call filter in a runtime configuration. Everything that's connected, for example, security, benchmarking, gas metering, it is all automatically done, and well, there's nothing for them to work on. So for them, it is very cheap, unless it's insecure to allow for this particular runtime call. And for you as a smart contract developer, well, you gain this advantage that your contract gains a lot of power. For example, it can stake on behalf of a user, or you can perform some vesting, well, just as a normal human user, right? On the other side, the problem is that, well, I will return 2 slides here, are these indices. Not only indices of this particular variance, but also the data, the call data, right? The problem that you might meet here is that if the runtime definition or this particular call transfer changes over time, that there is some runtime upgrade that, for example, changes, for example, the order of arguments, this destination and value, then your contract will be just broken. This call will not succeed because, well, it will be encoded to an invalid call object, or maybe it might be much worse, because, for example, if some indices will changes, you might accidentally call something completely that you didn't want, and, well, there might be a lot of mess. Of course, indices changes very rarely, and probably they shouldn't. So if they change, it's probably an awful terrible accident on the runtime side, or there is some there was some very big bug previously. But anyway, what you have to do actually is that you have to ensure that if your contract makes some runtime calls, you have to ensure that a part that translates call objects to that sends this call object to runtime is upgradable. So if you realize that a runtime will be upgraded and your contract will stop being compatible with it, you will have to upgrade this only this part that is responsible for encoding these code objects. Okay, this is very important thing to keep in mind. And the second very big disadvantage is that those methods that you can call from runtime from this user API cannot return values. The only thing that you will know is that if this particular runtime call has succeeded or failed. Unfortunately, in Substrate framework, for now at least, dispatchables, I mean, these user API functions, do not return any value. So with this mechanism, with this runtime call concept, you cannot query any storage, you cannot query any information from the runtime. This is a big disadvantage. As far as I know, there are plans to change it. However, it will not happen in the next few months at least. Okay, but, well, this is not the only option for you. There is the second mechanism called chain extension. Here it is. The chain extension, just to recap, is the concept that smart contracts are calling some functions in the runtime that are dedicated to just them. This is a logic. This will be the logic code that is not accessible by anyone but contracts. Okay, so here it is. Chain extensions are dedicated to smart contracts. Now, chain extensions require much more work to be implemented. And unfortunately, they require a lot of work, especially from the runtime maintainers. But anyway, chain extension has two sides. Two sides. One is inside, so the thing that you as a contract developer will interact with, and the runtime side, so it's actual implementation in the runtime. Now let's start with this inside part. So on the inside, there will be some chain extension trait. So basically a Rust trait that defines all the methods that are exposed by this particular chain extension. And, well, having it defined, we will include it in our environment. We'll see in a second, and then our contract will be able to call this chain extension, knowing what it exposes. Okay. On the runtime side, of course, we have to handle. This handling must be somehow implemented, and the logic itself must be provided. Let's start with this chain extension trait. So this part, this trait will usually be, or pretty always, will be defined and provided by the runtime maintainers. they will use this inc macro for chain extension. And in this example, we see outsource heavy crypto chain extension, which has just a single method called outsource, which takes some bytes and returns also some bytes. This chain extension has some identifier. And now there's of course some error codes here. For now, it's probably too much. And now let's consider how we can use it as a smart contract developers. So we can see we can depend on some library, some Rust library that provides this chain extension trait. And now when calling our contract, where we're implementing our contract, we'll have to firstly define an environment. An environment is another trait, inc trait. By default, there is something called default environment, and you are using it pretty much always implicitly. There is no way to import it or use it. However, if you want to use a chain extension, some particular chain extension, you have to redefine or create a new environment type that harnesses, that employs this particular inc trait. So for example, here we are creating a very simple environment with outsourcing, and we override just one type of it, associated type chain extension, with the imported outsource heavy crypto trait that we imported from runtime maintainers. And now the last thing that we have to do is that we have to make our contract aware of this environment, of the new environment, and thus making our contract aware of this chain extension. And we do it by specifying an additional argument to this in-contract macro, specifying that the environment that we are using is the new one that we have just defined. Okay? And once we have this environment brought into a scope, we can call this extension in a very similar way as we did before. So again, self.env, which brings us the environment, this object that provides these additional opcodes. Then we call extension. So we are saying that, well, we want to call an object that implements this particular chain extension, and then we are calling this typed method outsource with some input. Sorry, and essentially this is everything that you are doing on the inc side. So just to recap, we have to redefine this environment type, make our contract aware of this, or say that our contract uses this environment, and then in our message or in our contract logic, we are using this extension very similar to this runtime call or any other API that is provided from the runtime. Now, probably this is all that you will be working with, but just to give you some idea what has to be done on the runtime side, so just what are the trade-offs. On the runtime side, firstly, runtime maintainers or runtime developers have to implement some logic for handling all possible chain extensions. So, just to be clear here, a runtime might expose many different chain extension. Every extension can have multiple functions. So here we have to handle it if it's forbidden or allowed and things like that. Then if we are allowing for a particular function call, we are calling some internal logic, the logic that should stand behind this chain extension definition. The problem is here that chain extensions require their own security, benchmarking, and pretty much all the hard part has to be implemented for every chain extension separately. And this is the greatest disadvantage of the chain extension. I had worked with one. I was working with one chain extension, and I reassure you that it's an awful thing to do. It's very hard, especially because you have to manually ensure all the security issues, proper gas metering, benchmarking things, and of course you have to keep maintenance of this chain extension. So you probably won't see many chain extensions in the wild in production, but if you actually see one, it's probably very well maintained and it is very well tested already. And of course, there are already some of these. For example, assets extension is already used by some smart contracts. But well, it is this last part was just to let you know, just to keep you aware that chain extension requires a lot of much more effort from runtime maintainers than the runtime call does. Okay. However, well, having this cost paid, we get a lot of advantages. So, firstly, chain extension might provide contracts arbitrary logic. So actually, whatever you need, it can be implemented. And please notice that some things that will be executed in the runtime might be much cheaper than to do it in a contract. This is, for example, why we have this hash bytes or some signature, some cryptographic signature verification provided as an opcode. Because, well, if we are about to perform these things in WebAssembly, then the gas usage will be much higher. Okay. Now, because chain extension have control over pretty much everything, then we can have a customized weighting, limitations. Pretty much everything can be customized here. Of course, in a discussion, in a collaboration with front-end maintainers. This can be also a very nice way to wrap runtime calls. So, for example, if you want to get a return value from a runtime call, you can wrap it in a chain extension, and that way you can get a return value, or well, you can query anything. This is because chain extensions can return you any value that you can have. So, for example, in this outsource heavy crypto chain extension, we can see that our outsource can return actually some bytes, and thanks to that, we can query anything that is on chain. Again, an important notice that I was trying to underline here is that if you need some specific logic for your contract, you will have to discuss it and collaborate on it with runtime maintainers to provide it actually for you, and it might take time. And also because of that, as I previously mentioned, this chain extension trait that you would use in Inc contract would usually be defined and exposed by runtime maintainers, right? Because well, they have to maintain and implement both the interface that is exposed to contracts and the actual implementation on the runtime side. Now I would like to just tell you a short story. A short story from our own experience where we actually used chain extension, and it was a pretty day saver. Some time ago, like half a year ago, we were working on some ZK stuff in our smart contracts. Just to not go into details, our smart contract that was about to deploy had to perform some very heavy mathematical proof verification. It is usually a very heavy crypto, so the problem was that it couldn't have been done in WebAssembly, natively in the smart contract, because well, it took so much time that it was impossible to fit within a single block, and of course, it was extremely expensive. Therefore, we implemented a chain extension that provided to a contract this functionality that a contract could just pass a proof, this mathematical proof, to the runtime and ask the runtime to verify it. Okay. The problem was that even in runtime, it was too slow. And then, thanks to some other substrate functionalities, we are able to outsource this proof verification, this heavy crypto, even outside runtime. So to sum up, we are able to outsource computation, outsource very heavy, very extensive mathematics out from a contract through runtime to actually a host, the native binary that is running on a machine, on a bare metal. And of course, we could get the result back to a contract. This was actually sufficient, and well, this is probably the only way that you can perform very heavy, very extensive computations in a contract, just by outsourcing it either to a runtime or even further to a host. Okay, this is just the last message here, the last appetizer. It is possible. There are some plans to introduce a third mechanism for a contract. It is supposed to use the big concept of Polkadot called XCM, cross-contract message passing messages. Well, however, for now there is nothing available for smart contract developers. It is still in a planning phase, but probably in the next year, 2024, there might be some early concepts or early APIs that would enable your contract to actually make a use of the whole power of the XCM. And I think this wraps the whole topic. So are there any questions that I can answer?
Yes, there's been several questions actually came in during the presentation, but I know you're on single screen, so I did not want to interrupt.
Let me browse. Sorry, I've got a single monitor.
Yeah. The first one was from Mok, from on your very top. He was asking about runtime call.
Yes. That runtime call, the concept of the first was answered. Yes, this is we are accessing different families of functions in a runtime, so these are completely separate. Inc codec macro. Let me go back. Probably there is a typo if there is actually inc codec. No, there's a single codec. The thing is that right. One slide before here, where we pass this call object to a runtime, it actually has to be encoded as raw bytes, and then runtime will decode those bytes to its own interpretation of call objects. And for encoding and decoding things in the substrate world, we are using codec library. And when an enumeration enum type derives this encoding and decoding features, we can actually override what index a particular variant will have. And here we have to be compatible with with what index a particular palette or its call has. So this is the overwriting of an encoding object. Yes, this is very similar to, for example, CERD annotations and so on. Regarding accessing presentation, I will, of course, share it with Encode Club, and I guess it might be shared further.
Yes.
Are there any questions that I have missed?
Yes, in the question section, there's a couple.
Oh, okay. Sorry, I'm new to the whole applications. Okay, fee saving somebody instead of yes. So okay, it depends what we are Okay, so by fees, I would understand gas consumption, and the easiest heuristic here it would be that anything that is done in a contract will be much more expensive than doing this same thing in a runtime. So actually, if you can do anything in a runtime, by runtime call, it will be much easier than doing it in a contract itself. In a host function, yes, exactly. This is so answering the second. Yeah. The second question, this is exactly what we have done. We have prepared a very fast, very efficient, actually Rust math verification, proof verification, and we use it from the contract itself. Security concerns form, yes. So let me answer the last question and go back to security concerns. So Aleph 0 for now, at least on mainnet, we are not allowing for anything, I think. But for sure will be now whitelisting staking APIs. So there are some projects that are about to implement liquid staking, and for them specifically will open this call filter for staking APIs, so bonding, unbonding, nominating, and so on. Now, security concern with chain extensions. Well, chain extension. Chain extension, the implementation of a chain extension is put into a runtime. And the thing with code that is in runtime is that this code can actually access anything. So if your chain extension, okay, so this is the first concern. You have to be extremely secure and sure what you have implemented, because if there is any bug, it might affect arbitrary places in the runtime. Another security reasons are gas metering. You have to do it by hand manually. So for example, let me go to a slide. Looking for it here. Okay, this is some snippet presenting handling of chain extension, and this internal logic here. This internal logic invocation would normally point to the chain extension implementation itself, and it is a very common thing that this computation might fail in many different points. For example, when we had this example of proof verification, there were at least few points, few phases where this could have failed, and depending on that, we should have measured gas appropriately. So there was a lot of work to benchmark properly all the possible scenarios and to adapt gas metering to these failure points and things like that. This is actually, unfortunately, Substrat's framework doesn't give you that good API, that good tools for that. So it is very easy to introduce some hidden bug here. Also, there are problems with on this boundary. Let me go back to the onion diagram here. The problem is that things that are done in a contract sandbox are actually done in a very different world that the runtime operates in. And this boundary that they are trying to, by which they are trying to communicate, is very primitive and raw. Everything there are just bytes, and everything is encoded just with integers. And when implementing a chain extension, there are a lot of things, at least at a few points like this, that we do not work with typed API. We are working with integers and status codes and things like that, which make the whole experience, the whole concept extremely complex. There's a very high complexity on a very low level, which might is bug prone. So these are the main security concerns here. I hope this answers at least partially. We have gone through all of them, right? From all questions. Oh, so there's one. So sorry. New JSON RPC. So end users, if I understand correctly, end users cannot access chain extension. Chain extension is pretty much invisible for anybody who just sends a transaction to a blockchain. Chain extensions are visible just for contracts. So in particular, there is probably no much sense in working with JSON RPC endpoints via chain extension because it would have to be called by a contract. And well, smart contracts do not return values. I mean, unless it is a dry run. So probably this is not the way to expose new JSON RPC endpoints. Well, yes. Okay. Regarding XCM, I know not very much on this matter, unfortunately. So I cannot say exactly if we could substitute it with this one. But as far as I can say, if you have XCM, you do not have to hack around it. However, it still doesn't invalidate the need of chain extension. Okay, yes, that's correct. However, okay, so answering regarding the current state, yes, chain extension can access anything in the runtime. So yes, you are right, including XCM. So you can actually use XCM through this chain extension. But as far as I know, to the best of my knowledge, the XCM support for contracts will be done separately, natively, without chain extension. But it is to be done to be provided. I don't know, can't say soon, but I guess it's like is next year. So probably it makes more sense to wait for that than work around now. Yeah. Yes. The whole ink and smart contract world is evolving. So yeah, the future will be better, of course. So it seems that we are done with all the questions as far as you can see.
Yeah, and thank you for answering these, and thank you, Mork, for asking these great questions, and also the rest as well. But
thank you very much.
Questions one. Cool. I think that is the majority of the questions. I mean, most of them pretty much have been answered. I hope everyone appreciated the responses. And again, all of this will be recorded and it will be posted tomorrow. So if any of the explanations you thought you need a bit more time to grasp, you will be able to just go through the recording tomorrow and get a deeper understanding of it. Thank you once again, Piotr, for the presentation and the great explanations in the end.
Thank you very much. It was
great to see you all in 40 minutes for the second workshop. And thank you for participating.
Thank you very much. Bye.
See you all soon.